This is our 10th lecture. I've updated the schedule, the tentative schedule, so now it makes sense. We're in section 3.2 of the book, so today we're supposed to look at limit theorems, so theorems that let us compute limits. Last time we did the definition of a limit, and I've copied it down here to save us some time. A really important definition. We've got a quiz next week, and you're guaranteed that there's going to be questions about limits on the quiz. Okay? Now, I'm going to join this Zoom with my desktop just in case. Read the definition. I'll be right back. Okay. Oh. Jeez. Are you still there? It says that I'm not still here. Perfect.
I can hear you.
Okay. Okay, sorry about those technical issues. Are there any questions about this definition before we go on? And we need to do some examples and then prove some theorems. And then hopefully we have time to go back to our examples and do some more. Okay. You know, the key with this theorem is the quantifiers. For every epsilon, there is an n. Okay. So, we're given the epsilon. In fact, all of our limit proofs are going to start with, let epsilon greater than 0 be given. And we have to find the capital N that gets the terms of our sequence within that epsilon of the proposed limit. Okay? This must be by far the most important definition in this course. And in fact, this is what separates how we approach calculus nowadays from how Newton and Leibniz approached it back in their day. Okay, they didn't have the notion of a limit, and so their arguments get a little bit wishy-washy when it came to things involving limits. Okay. Examples, I want to start out with two of them. The first one, the limit as n goes to infinity of 1 over n is 0. Okay. Proof. Let's start out with a standard limit argument. Let epsilon greater than 0 be given. Now, let's go over here on the side. This is just going to be scratch work. Okay, this isn't the proof of the limit. We're just going to go over here. What do we want? We want 1 over n minus 0 to be less than epsilon. Okay? Absolute value of 1 over n minus 0 to be less than epsilon. Well, the absolute value of 1 over n minus 0 is just 1 over n, because n is a positive integer, so we want that to be less than epsilon. Right? So we want n to be greater than 1 over epsilon. Okay. Now, why is there a natural number n that is greater than 1 over epsilon?
Don't we have a theorem that says says that. I don't remember which one it is.
Mm-hmm. It's the Archimedean property. Okay? So, and this is, one of the few uses of this property, by the Archimedean property, because usually when we use it, we just don't bother saying it. There is some capital N in the natural numbers, so that capital N is greater than 1 over epsilon. Okay? Let's go back to the definition of the limit and look at it closely again to just double check what we have to do. For every epsilon, that's why we started our proof with let epsilon be given. So our proof will hold, if it holds for that epsilon, it will hold for all epsilons, because we didn't make any assumptions about that epsilon. Then we have to show there is a capital M. Well, we found a capital N. And now we just have to check that we have this absolute value of xn minus x less than epsilon for all little n greater than or equal to capital N. Okay? So the next step in our proof is we're going to look at, not that inequality, we're going to look at the quantity xn minus x, absolute value. Okay, and we're going to look at it for little n at least capital N. Okay. For little n that are at least capital N, we have, what do we have? The quantity we're interested in is 1 over little n minus 0, absolute value. Okay. We already said in our scratch work that's equal to 1 over n. Okay. N is greater than or equal to capital N, so this is less than or equal to 1 over capital N. And capital N is greater than 1 over epsilon, so this is less than epsilon. And I'll put a little as desired at the end. That's what we wanted to show. Okay. Any questions on that proof?
I have a quick question about the limit definition. Why do we want it to be less than strictly less than epsilon instead of just less than or equal to epsilon?
I think the actual answer to that question is that it's slightly easier to write a less than a less than or equal to. And over the course of an entire career in advanced calculus, you just save a few of those lines underneath the less than. No, mathematically that's the same thing. Any other questions?
So just like overall, this is just a proof that this fits in the definition of a limit?
Yeah, we proved that the limit is 0.
Okay, thank you.
Okay, and now, unless the question is literally prove that the limit of this sequence is 0, you're allowed to use this fact. Okay? We're going to do one more example and we'll get onto our theorems. Limit, let's make this a little bit more complicated. 2n plus 1 all over n plus 5. And we should say as n goes to infinity, what is this equal to?
2.
2. Good. Now, that's basically a guess. Well, it's an educated guess, I hope. How would we go about proving that? Okay.
Or just take a fixed epsilon, right?
Mm-hmm. I'm going to do a slightly different proof structure here. Just to show you that, okay, the first line of your proofs doesn't literally have to be let epsilon greater than 0 be given. You can make that the second or the third line too. So what I'm going to do here is I'm going to do my simplifications first. Okay. What's the quantity we care about? It's that. Right? It's our sequence minus our limit, absolute value. Good. And now, what I want to do is factor an n out of both sides of that fraction. Okay? So this is the absolute value of 2. In fact, let me pull that 2 out. 2 times 1 plus, let me show you all the steps here. 2 times n over n times 1 plus 1 over 2n all over 1 plus 5 over n minus 2. We agreed? Now we know a little bit about properties of absolute values. Those 2's can come out. So this is 2 times, and now you have this mess, 1 plus 1 over 2n over 1 plus 5 over n minus 1. Okay? What are we going to do with that? Well, this is where limits get messy. We go over here and do our scratch work. We're going to say, what do we want? We want this to be less than epsilon. Oh, why did I think about trying this example this way? You know what? Here, let this be a lesson to you. The limit theorems we're about to prove are very useful. They're going to make this limit really easy. But if you try and do it from the definitions, straight from the definitions, it's not so easy. Okay, because now we have to go over here. Oops, and we actually wanted a 2 there. Right? We have to go over here and solve this inequality. I mean, so we'll be doing things like minus epsilon is less than 2 times 1 plus 1 over 2n. Okay, and we'll be trying to solve this. It'll get pretty messy, I think. Okay. So let's just prove some limit theorems, and then we'll do this. As soon as we've got the theorems to do this, with theorems, we'll come back to it, okay? So, here we've kind of got two big theorems today. Here's our first big theorem. If you look in the book, this is kind of 3.2.3. Let's start with two real valued sequences. So xn and yn be real valued sequences. And I'm gonna suppose they both converge. So I'm going to suppose that xn converges to x and yn converges to y. Then and now I'm going to tell you the limits of a bunch of related series. Number one, if we put a negative sign out front of x, that converges to, any volunteers?
Negative x.
Good. Number two, if we take the absolute value of xn, that converges to the absolute value of x. Number three, let's add them together. That converges to x plus y. Number four, let's multiply them. That converges to xy. Okay, the point of this theorem is to say that limits cooperate nicely with all of the field operations we'd want to do in the real numbers. So what do we need next?
Division.
Division. But division's a little bit of a problem because you can't divide by 0. Think about just the sequence 1 over n. Well, I guess that wouldn't be fair because the sequence xn equals n doesn't converge. But anyway, we need to say something
Scaling the
here.
sequence?
What's that?
Scaling the sequence?
Oh, scaling we'll get from 4.
Uh-huh.
If you let yn be a constant sequence, then you're allowed to scale the sequence from 4. Yeah. What we're going to say in 5, and we could say in 5 that xn is never 0, but actually it suffices to say that if the limit is not 0. Okay, then the reciprocal sequence 1 over xn converges to 1 over x. Okay, so let me add in here 1 over xn is defined for, here's a phrase that we'll be using a lot. 1 over xn is defined for all sufficiently large n. That's a way to say that there exists some capital N such that for all little n, at least capital N, this happens. Okay. And the point is, if your limit is not 0, then eventually your sequence has to stop being 0. Okay? Because eventually your sequence has to be close to its limit, and its limit is not 0. Okay? Now, hopefully you can see from this theorem that this will give us all the arithmetic we want. Since we can do negatives, we can do subtraction. Since we can do reciprocals, we can do division. Well, that's all the arithmetic we'd want, right? Now, in terms of a proof, this is proved in all its detail in the textbook, of course. We don't have time to go through really formal proofs for all of them, but let me just kind of indicate what's going on. In number 1, we have we want to show that minus xn converges to minus x. Well, that means we want to look at, we want to look at the absolute value of minus xn minus x. Okay. That's the same thing, though, as the absolute value of xn minus x. Okay. So now, morally the point is that the xn sequence converges to x. So we know we can make that small. And making that small is the same as making the quantity we care about here small. So we can make the quantity we care about here small. Let's do a formal proof of this one, and then I'm going to skip the formal proof of the next one. And maybe the one after that. So here's the formal proof. Let epsilon greater than 0 be given. Okay. Because the sequence xn converges to x, what does that mean? By definition, that means that we've got our capital N. So there is a capital N in the natural numbers such that xn minus x is less than epsilon for all n at least capital N. Therefore, the quantity we care about is also less than epsilon. For all little n greater than or equal to capital N. Any questions on that one? No? Okay, the second one is the absolute value. The absolute value means the quantity we care about is the absolute value of xn minus the absolute value of x. Close absolute value. Okay, I'm gonna be putting some argument above this line, so I'm leaving room. What can we do with this quantity based on things we know?
triangle inequality.
Mm. Yes, so we're going to do the triangle inequality. And what does the triangle inequality tell us?
Less than or equal to the absolute value of xn plus the absolute value of x.
That version isn't going to work too well. Oops. So yes, the one version of the triangle inequality, the standard version, tells us this. But that's not going to work too well because maybe that, if the limit, if x is large, then this quantity is never going to be small. There's another version of the triangle inequality that will help us here.
It's less than equal xn minus x. And that's it's corollary 2.2.4 in the book, if you guys want to look at it.
Yeah, but I would rather explain it geometrically, okay? So this is true on the real line, although it's also true in the plane. So in the plane with the Euclidean norm, this is also true. But let's see, we'll look at it in the real line. Here, the magnitude of xn minus the magnitude of x, this is how much longer is xn minus x. How much longer is xn than x, okay? An upper bound on how much longer x, or how much larger xn is than x, is how large their difference is, okay? This is an equality if they're pointing in the same direction. Okay, I guess I'm using the plane explanation, but in the real line it's even simpler. If xn is here, and x is here, and x is here, and then on the left we are computing the difference in their magnitudes, and on the right we're computing the absolute value of their difference. They're the same thing here. Okay? If they happen to go in the other way, so if x is over here and not over there, then on the left we're computing the difference between their magnitudes. That's still this small number because now this is absolute value x. And this was absolute value xn, which is the same as xn, we're saying. But on the right-hand side of this inequality, now we're computing the magnitude of their difference, which is this much longer distance. Okay? So personally, I actually have a problem remembering this inequality in the real line. I think it's a lot easier to remember in the plane, is that in the plane, it says that the difference between their magnitudes is at most the magnitude of their difference. Okay. Oh, with equality, actually in the plane you can say with equality if and only if they point in the same direction. Okay. Oh, right. That was quite a tangent. Let's see. Now we see that actually you just go back to the proof above. If we make the absolute value of xn minus x small, that will force the absolute value of, well, it'll force the left-hand side small too. Okay. So now you literally just, to finish the proof, you have to copy. Well, basically take that, copy it, put it in here. Change that part out. Okay. Questions? I'm going to rush through addition because the other two are a lot more interesting, I think. So again, I'm not going to write a complete proof for addition. We just don't have time. Again, think about what we want to make small. We want to make this small. Xn plus yn minus x plus y. Okay. We can regroup that. Okay, regrouped now. And now how would we bound that absolute value?
Is it less than 2 epsilon?
Oh, I think you're thinking ahead of my question. Yeah, if we'd made both xn and yn get within epsilon of their limits, then we'd have a 2 epsilon here. I'm just saying, how would we bound this absolute value? Don't think about epsilons yet.
Triangle inequality?
Yes. And the normal form of the triangle inequality, not the form we just used. Oops. Okay. Now, morally, we're done. Xn converges to x, yn converges to y, so everything on the right-hand side can be made small. That means the left-hand side can be made small. Okay. I said we're going to brush over this proof. Let me spend a couple more minutes. Let epsilon greater than 0 be given. Okay. Now, we're going to get a capital N from the xn's and a capital N from theyn's. And it's important to remember in that definition of a limit, epsilon is just a variable. Okay? So now I get to use the definition of a limit because I know xn converges to x. So instead of insisting that xn be within epsilon of x, I can insist that it be within epsilon over 2 of x. Because the definition of limit said for any epsilon. So I'm going to take... And again, you never want to write this. You never want to write like set epsilon equal epsilon over 2 because that makes no sense. Right? But what I'm thinking is that variable in the definition, I want that variable to be epsilon over 2. Okay? I want it to be this epsilon divided by 2. Okay? So, because, and now I'm going to use the shorthand for convergence, and that's okay. Because xn converges to x, and yn converges to y, there are numbers nx and ny in capital N such that for little n, at least capital N sub x, okay, so this is where I said I want to force this to be less than epsilon over 2. And that's okay. I just go to the definition. The definition says, how close do you want to be? And I say epsilon over 2. It gives me a capital N. I'm going to call that capital NX. I'm going to do the same with y, and I'm going to get a capital NY. Okay. Now, I'm gonna have to scroll up here in a second. Let's just not forget where we are. The quantity we want is at most the sum of these two things. For little n sufficiently large, we've made both these things smaller than epsilon over 2. So as long as we satisfy both of these inequalities on little n, we'll get that the quantity we really care about is less than epsilon. Okay? So let's scroll up and write the end of the proof. Now, we want to produce a capital N. What should our capital N be?
Max of nx and ny.
Yes, we will take the max of them. Let me just make an editorial comment while I write max here. Your book uses supremum for everything. It would be technically correct to write a supremum here. I actually go the other way on this. If I've got a finite set, then I write maximum because it has a maximum. Okay. The whole point of supremum is that arbitrary sets of real numbers don't have a maximum necessarily. Okay. For little n greater than or equal to capital N, we have, this is what we wrote above. We have our inequality, and we get less than epsilon. Questions?
So here where you made it for the individual x and y bounded by epsilon over 2, by the definition, if you just bounded those by epsilon and then had this last inequality be bounded by 2 epsilon, it would still fit the definition of the limit, right? For any epsilon?
I would argue technically not. We're saying, the definition says, give me an epsilon, and I'll give you a capital N.
Mm-hmm.
That works. So I think you when you write one of these proofs, you have to say, you give me an epsilon, I will give you a capital N where I'm less than epsilon, not less than 2 epsilon. Okay? Morally, 2 epsilon works, but then just go back and divide by 2.
Thanks.
Mm-hmm. Okay, multiplication's a little bit more interesting. What was multiplication? That was number 3? No, it's number 4. Okay. What can we do? Again, we'll start out playing with the inequality and see what we can do. That's the quantity we want to make small. I don't think it's obvious how to make that small. Except that, either way, there's going to be some slightly messy algebra, okay? What I'm going to do, because I've already worked this out before. If you add this middle term and add and subtract this middle term, then actually things get better. Okay, and the reason things get better is that now, over here on the left, I've got an xn in both terms, and then I'm looking at, so on the left I'm looking at an xn times yn minus y. And I know yn minus y is going to get small. Okay. Over here on the right, I'm looking at a y times xn minus x, and we know xn minus x is going to get small. Okay? So now we're going to split them up using the triangle inequality, just like that. So I'm going to have an xn over here times yn minus y plus a y times xn minus x. Okay, now we know, because our rules of absolute value, we can break these absolute values up. Now, let's look at this. Let's highlight in green the things that are going to be small. We know yn minus y is small. We know xn minus x is small. Okay. Now, where are our questions? Questions are xn and y. Okay? Except this absolute value y is just some real number. Okay? So when xn minus x gets really small, multiplying it by an absolute value of y won't change the fact that it's really small. So actually, I'm going to change that one to green because that's okay. Now we come over here. The problem is this xn is changing. That changes as n changes. So we might have the case that we've bounded the yn minus y, but because we're multiplying by an xn, we're taking a small thing and making it big. So this is our challenge. We need to get some control over the xn, and let's do it. Okay. Because xn converges to x. Think about that definition. There is some, instead of a capital N, I'm going to do a capital M. And what do I want? I'm going to actually insist that I have that inequality. There's some capital M such that eventually we're less than our limit plus 1. Okay. Now, how would I formally get this from the definition of the limit? Well, the definition of the limit would say that we get the absolute value of xn minus x is less than 1. Right? But this is greater than or equal to the absolute value of xn minus the absolute value of x. Okay, so this thing right here is sandwiched between a -1 and a 1, and play around with it. We'll get the inequality we want. Okay? Now, oh, I see. Okay, well, anyway, we'll go with the variables as they are. Now, set C, capital C, to be the maximum of the absolute value of x plus 1 and the absolute value of y. Then for n at least capital M, what do we know? The quantity we care about is less than or equal to both the xn and the y terms are less than or equal to c, sorry. And then what do we have? An xn minus x plus a yn minus y. Okay.
So what exactly is happening here? Can you scroll up a bit?
Yep.
So you're saying that we're like distributing out the xn and the yn, but we're taking the max of them.
Yeah. So
Yeah.
these terms are at both at most capital C. So I'm saying that's at most capital C times absolute value yn minus y. That's the most capital C times absolute value xn minus x. And so together, we get at most capital C times the sum of those two things.
Okay, I see now.
Now, if we want this to be less than epsilon, then we want the xn minus x absolute value to be less than epsilon over 2c. And we want the yn minus y absolute value to be less than epsilon over 2c as well. Okay? So, and I realize I'm going to go about 5 minutes over, but I want to finish the division case. We'll sketch the division case as well. But if you have to leave, of course, that's understood. Nx and ny in the natural numbers, such that for all n at least nx, xn minus x is less than epsilon over 2c. And for all n greater than or equal to ny, I can make the same claim with the y's.
Shouldn't we pick these n's greater than m so that this inequality is going to hold?
Oh. I don't need to right now.
Okay.
But I do need to by the end.
Okay.
So now I'm going to set capital N to be the max of everything. Okay. So that's what we do. At the very end, we say, okay, we needed n, little n to be at least capital N sub x, and capital N sub y. So we'll make our capital N be the maximum of those three. Okay. Questions?
I don't quite see why we have to pick them. I see why we have to pick the max of n, x, and n, y, but I'm not sure why we have to include m net max.
But that's because we need little n to be at least capital M, so that we get the bound we really want. So if we added in an extra line here, we would say less than or equal to c times and then that's less than epsilon. Okay, and it's this part that we need the little n at least capital N. Okay, so again, I'm sorry for running over, but I really do want to finish the reciprocal part. In the reciprocal parts, what do we know? Xn converges to x, which is not equal to 0. Okay. Since this is true, there is a capital N sub 1 such that for all little n at least capital N sub 1, the absolute value of xn is at least 1/2 the absolute value of x. Okay. I'm combining a couple steps here. One of this is we know that the absolute value of xn converges to the absolute value of x. That was part 2 of this theorem. Okay. Well, if we know that you converge to the absolute value of x, then, you know, by the definition, for every epsilon, there exists a capital N. So I'm just going to choose my epsilon to be the absolute value of x over 2 in the definition of the convergence of this sequence. Okay, and then if I'm within absolute value of x over 2 of absolute value x, I'm at least 1/2 the absolute value of x. Okay. So for these n, we have 1 over the absolute value of xn is at most 2 over the absolute value of x. And that was an n1 up there. It's an n1 and a comma. Okay. So again, for these values of x, the quantity we care about, these values of n, sorry, the quantity we care about is 1 over x sub n minus 1 over x. Okay, well, we want to combine fractions. We cross multiply. We get an x minus xn over their common denominator, x times xn. Okay. Now, we pull out the 1 over absolute value xn times x, and we're left with a quantity that's small, a quantity that we can make small, times the quantity that, well, now we think about it, the x part of this is just some number. And the xn part of this, we've just bounded. The 1 over xn part, we've just bounded. Okay? So this is less than or equal to 2 over the absolute value of x all squared times xn minus x. Okay? This holds for n at least n1. Now, choose an n2 to make this quantity, the absolute value of x minus xn minus x, to make this quantity small enough. What is small enough? It would be less than 2 epsilon over absolute value x squared. Okay. So choose capital N2 so that I said that backwards. Choose N2 to get that, and then set N equal the max of the N1, N2. So for a little n, at least capital N, we have well, since little n is at least capital N1, we get this inequality. Since little n is at least capital N2, we get this inequality. You put them together and we are less than, everything cancels but the epsilon, as desired. Okay. Last thing, I wanted to go back to that example that we skipped, and I said we'd come back to it. This was example 2 from before. We were looking at the limit of 2n plus 1 over n plus 5. Now you can do what you want to do. We have 2n plus 1 over n plus 5. Now we can't do a division thing here because the limit of the numerator is infinity and the limit of the denominator is also infinity. But we can pull out a 2 and an n over n like I did before. 1 over 2n. Okay. Now, the n over n is just a 1. The 2 is just a 2. Okay, by our arithmetical properties of limits, the limit of the sequence is the limit of the constant sequence 2, which is just 2, times the limit of this sequence on the right. Okay? The limit on the sequence on the right is the limit of the numerator times the reciprocal of the limit of the denominator. Or we could just say the limit of the numerator divided by the limit of the denominator. Okay? If we want to further break it down using that theorem, the limit of the numerator is 1 plus the limit of the sequence 1 over 2n. Let's break it down one more time. The limit of the sequence 1 over 2n is 1/2 times the limit of the sequence 1 over n. And we did the limit of the sequence 1 over n at the beginning of class. Okay. So here in the numerator we get a limit of 1. In the denominator we do the same thing, except we come over here, 5 over n, that's the limit of 5, the constant sequence 5, times the limit of 1 over n, and that limit is 0 as well. Okay, so this limit is equal to 2 using the theorem we just established. Okay, so now thanks to that theorem, you can do all the arithmetic that you're used to doing with limits. And I'm sorry for running actually 12 minutes over. I will definitely stop here.